Once I showed you how to solve this sum. It actually goes to pi squared over 6. But what's really cool about it is there's a much easier way to solve it than the way that Euler did. Above is Parseval's theorem, which is actually a consequence of the Fourier series. If we have a function f of x, which is represented by this Fourier series, and just assuming that L is equal to pi, then 1 over pi times the integral from negative pi to pi of f of x squared is equal to a naught squared over 2 plus the sum going from 1 to infinity of the Fourier coefficients squared. So let's see this theorem in action. Recall that with L is equal to pi, we showed that x is actually equal to the infinite summation from n equals 1 to infinity of 2 times negative 1 to the n plus 1 over n times sine of nx. So let's just plug it into the identity. 1 over pi times the integral from negative pi to pi of x squared dx. We know that this integral is pretty trivial. It equals 2 pi squared over 3. And on the other hand, we just have the square of the Fourier coefficients. That negative 1 term will just always be positive once we square it, so we get 4 over n squared. So then when we put our solution to the integral here and we pull the 4 out of the sum, we get the classic beautiful result that pi squared over 6 is equal to this infinite summation. So there you go. Parseval's theorem took this problem that's really hard and just split it right open. That's incredible.